In this video, I'm going to be talking to you about the null space of a matrix. So I'll figure I'd start with the definition. If A is an m by n matrix, then the null space of A is the set of all vectors in Rn for which A times x equals 0. It's like the set of all zeros of a matrix. Now, by this point in the course, we've actually been computing this quite a bit. We've solved homogeneous systems. We've row reduced to figure out, the solutions to the equation Ax equals 0. And now we have a name for it. It's called the null space. I will also mention that, some textbooks, some people, and some other places, they might call this the kernel. The kernel of A. But let's just go and let's compute a couple of these. All right, so for example, let's just, find the null space of this matrix A. Okay, and I'm going to find that by solving the system Ax equals 0. So what I'm going to do is I'm going to take A, augment it with 0, and row reduce. Okay, so I'm going to add one copy of row 3 to row 1 to row 3. So I'll get 0, 2, negative 2. I didn't change anything here. 1, 0, 1. All right, and then I'm going to, maybe I'll go up here so I have room to write my solution. I'm going to add, or subtract 2 copies of row 2 from row 3, and I'll have 1, 0, 0, 0, 1, 0, 1, negative 1, 0, and a column of zeros. Right. That means that x1 plus x3 equals 0, meaning x1 equals negative x3. Oh, I'm outside my shot. Hold on. Yeah. Barely. Okay, x2 minus x3 equals 0, and x3 can be whatever it wants. It's unconstrained. So what I'm going to say is that the null space of A is equal to the set of all vectors x in R3 for which, hold on, what am I doing here? Oh, yeah, x equals, x1 is equal to negative x3, x2 is equal to x3, and x3 can be whatever it wants. Okay, so it's the set of all vectors like that. You could also say it's all the scalar multiples of the vector negative 1, 1, 1, by factoring out that x3 if you like. All right. Now I want to do one, I'm going to do a 2 by 2, and the reason I want to do a small one like this is that the columns here are pretty clearly independent, right? I'm not going to have that row of all zeros at the bottom like I did in the first example. Okay. And so what's going to happen is I'm interested in finding the null space of B. So I'm going to solve the equation Bx equals 0 by taking B, augmenting it with 0, and row reducing. So that'll be 1, 0. 5 minus 6 is negative 1. Okay. Might just add 3 row 2s to row 1 right now, and then divide row 2 by negative 1. And then I'll see, oh, okay, cool. I've got x1 equals 0, x2 equals 0. Okay, so the null space of B is just the set that has the 0 vector in it. Okay? But we've seen this already before. When the only solution to the matrix times x equals 0 is when x is equal to 0, we said that that matrix was non-singular, provided it was squared. So notice that non-singular is the same as having a null space that is just the 0 vector. So if the matrix is square and its null space is just only the 0 vector, the singleton set 0, then that square matrix is non-singular. All right, now let's look at some non-square matrices and see kind of how this plays out, right? I know that solving the system Cx equals 0 is like solving a homogeneous system with fewer equations than variables. So I know there's going to be infinitely many solutions. So I know that this null space is going to have to be bigger than just the 0 vector. But how that's going to go, who knows? Let's actually row reduce the thing. So we're going to take C and we're going to augment it with 0. And I'm going to row reduce. So I'm going to start by taking row 1 and adding it to row 2. and 2, 5, augmented with 0, 0. Now I might subtract row 2 from row 1 to get rid of that one up there. And then I'll have that. 2 minus 5 is negative 3. This is going to be a 5. All right. Okay, so I've got in reduced echelon form. I just need to interpret my solution and write down my null space. So I've got x1 minus 3x3 equals 0. And x2 plus 5x3 equals 0. Looks like x3 can be whatever it wants. So I'm going to say that the null space of matrix C is going to be the set of all vectors x that are three-dimensional, because I've got 3 columns in my original matrix, and because I've got 3 variables that I'm kind of dealing in my solution space off to the left. Okay, so it's the set of all x and R3 for which x equals 3x3, and maybe this time I'll factor out the x3. Right? Factor out the x3, and I'll have 3x2 is negative 5x3, and x3 can be whatever it wants. Okay? Where x3 is some real number. Okay? And that's the null space. It's the set of all multiples of 3, negative 5, 1. So it's like a line's worth of points. Right, now let's look at a tall matrix and see how this is going to go, right? This is clearly 2 independent columns, and let's just have a look at this and see what's going to happen. If I want to find the null space of D, I'm going to augment this with the 0 vector. So 1, 0, 1, 0, 0, 1, 0, 1, augment with 0, 0, 0, 0. And we're going to row reduce, right? But this will be pretty easy because I know how this is going to row reduce. Pretty easily. And so that's going to be x1 equals 0 and x2 equals 0. Okay, those bottom rows of zeros are just really not telling me anything because there's only 2 variables of information, right? So what I'm going to say is that the null space of matrix D is equal to the set that has just the 0 vector. Now, this is not enough to say that D is a non-singular matrix, because D is not a square matrix, so it wouldn't make sense to say if it was singular or non-singular, right? Right, now the last thing I need to show you is this theorem, that the null space of every matrix is always a sub. And I'll do this by checking the 3. First, the 0 vector is in the null space, because if I take the 0 vector and I multiply it on the right, to A, that's always going to give me back the 0 vector, which means that the 0 vector is part of the null space. Second, I need to check that the null space is closed under addition. Okay, so if I have 2 vectors that are in the null space, then if I take them and I multiply them on the right of A, I'm going to get 0 for both of them, right? But I also know about the distributive property, right? The distributive property holds for matrix multiplication. So if I take A and I multiply it on the left of x1 plus x2, I'm going to get ax1 plus ax2. I know those are zeros. 0 plus 0 is still 0. Okay? This means that x1 plus x2 is in the null space. Now last, we have to check scalar multiplication. So let's start with the vector that's in the null space and figure out what happens when I multiply it by a non-zero constant. Is it going to still be in? Okay, when I take A and multiply it by k times x1, I'm proposing that that's the same as k times A multiplied by x1. Because the function, f of x equals A times x, with A being this matrix, it's a linear transformation. And this is one of the properties of linear transformations, that f of k times x is k. So since we know that matrix multiplication constitutes a linear transform, we can factor out that k. And since we know that ax1 is equal to 0, this is k times 0, which is 0. So that means that kx1 is also an element of the null space. And since all 3 conditions are met, we've shown that the null space of A is a subspace. That's all I got for you for this video.